The impact of the underlying risk in control group and effect measures in non-inferiority trials with time-to-event data, a simulation study. This presentation is based on our publication in the Journal of Clinical Medicine Research. I will start with the background of this study. A non-inferiority trial is used to examine whether an experimental treatment is no worse than an active control, usually the standard treatment used in practice. A non-inferiority trial is usually conducted when investigators expect an experimental intervention has potential advantages over the standard treatment, but they do not anticipate that the experimental treatment will be superior to the standard treatment in the primary outcome. The upper or lower limit of the 95% confidence interval of the estimated treatment difference will determine the conclusion of the non-inferiority trial. The underlying risk will largely affect the upper or lower limit of 95% confidence interval in a non-inferiority trial. Then, an interesting question arises. When the true difference between the experimental intervention and the active control is small, how would the conclusion of a non-inferiority trial change if the observed risk is different from the risk assumed in the trial's design? I will present the methods of this study. Let T and C represent the values of an effect measure for the efficacy of an experimental treatment and an active control treatment, respectively. M is the predefined non-inferiority margin. The standard null hypothesis and alternative hypotheses for non-inferiority test can be expressed as shown in the slide. The expression above assumes that higher values of T and C indicate better efficacy outcomes. Different effect measures, such as absolute difference or ratio, and outcomes, favorable or unfavorable, may be expressed differently in null and alternative hypotheses. We simulated time-to-event data with true hazard ratio of 1, the base case, and 0.95 and 1.05 in sensitivity analyses for experimental treatment versus the active control treatment. The hazard ratio measures an undesired outcome. We selected two effect measures, hazard ratio and the difference in two Kaplan-Meier estimators at 5 years. Since the true hazard ratio is 1, or close to 1, the correct decision is to reject the null hypothesis. If the null hypothesis is not rejected, it would be a type 2 error. Statistical power or 1 minus type 2 error rate was estimated for different effect measures at various categories of underlying risk in a hypothetical control arm. We simulated the Weibull distribution time to event data. We illustrated the simulated survival data in this figure. We simulated 10,000 hypothetical trials to cover the underlying risk from 0.03 to 0.95 in 5 years in the active control group. 600 patients were generated for each hypothetical trial. Patients were randomly assigned to the experimental group or control group with a 1-to-1 ratio. We selected gamma equals 2 for both groups, setting the hazard to increase over time. We also considered random censoring in the simulation. The SARS code used for simulating time-to-event data can be found in Appendix 2. If the 95% upper limit of an effect measure, measuring an unfavorable outcome for the experimental intervention, or the 95% lower limit of the effect measure, measuring a favorable outcome, fell within the predefined non-inferiority margin, we concluded non-inferiority. Two effect measures were investigated. The fixed margin approach is recommended by the United States FDA and widely adopted. We selected the empirical non-inferiority margins, based on a systematic review of non-inferiority trials. I will present the results of this study. This figure shows the plot of upper limits of 95% confidence interval of hazard ratio against follow-up time for a true hazard ratio of 1. Each dot represents one simulation and the line is the predicted line fitted by a non-parametric regression model. In summary, the upper limit of 95% confidence interval decreased sharply when the underlying risk was between 0.03 and 0.25, and then gradually decreased until the underlying risk reached 0.95. When we use the empirical non-inferiority margins, the probability of concluding non-inferiority would increase as the underlying risk in the control increased. The same pattern was observed in the plots of true hazard ratios of 0.95 and 1.05. Using the empirical non-inferiority margins chosen, hazard ratios of 1.2, 1.35, and 1.5, the probability of rejecting the null hypothesis when the underlying control risk was less than 10% was small, 0.067, 0.131, and 0.224, respectively. Such probability increased as the underlying risk increased. Compared with hazard ratio, the 95% upper limit of the difference in two Kaplan-Meier estimators showed greater variability. Shown in the fitted curve, the predicted 95% upper limits of the difference in two Kaplan-Meier estimators gradually increased, as the underlying risk increased and reached a maximum at an approximate control risk of 50%, and then decreased afterward. When we use the empirical non-inferiority margins, the probability of concluding non-inferiority would decrease as the underlying risk in the control increased. In such case, the probability of concluding non-inferiority was at a minimum when the control risk reached about 50%, and then increased as the control risk increased. Conclusions. When hazard ratio is the effect measure, the probability of concluding non-inferiority will increase as the underlying risk in the control group increases. When the difference in two Kaplan-Meier estimators is the effect measure, the probability of concluding non-inferiority will decrease as the underlying risk in the control increases. The probability of concluding non-inferiority is at a minimum when the control risk reaches about 50%. When the risk in the control arm is less than 10%, the conclusion of a non-inferiority trial is sensitive to the choice of effect measure. Here is the timeline of this article. Thank you.